This one, moment of inertia. Okay. Alright. So let's continue. Okay, we go from here onwards. So kita akan masuk chapter 7 ni minggu lain lah. Okay. Alright. So let's recap a bit. When we talk about moment of inertia ni, benda yang kamu kata resistance to angular acceleration tadi, this moment of inertia representing weight, representing mass of an object, and this mass is the mass of that object during a rotational movement. Okay. Video yang itu kamu dah tengok kan, yang dia berpusing-pusing tu. Sekejap
Video dah sir.
Dah kan?
Cikgu.
Yang cikgu dia berpusing tu.
Dah.
Okay, so they prove that if the radius of rotation, if the radius, okay, dia punya jejari tu besar, the rotation is going to be slower compared to if the radius is shorter. Jadi apa yang kita nak buktikan dekat sini ialah when we do rotational action. Okay, when we do rotational action, let's say we take example of our own hand lah. Okay, kita ambil tangan kan. We take the hand holding an object. If we try to move an object, kita namakan jarak ni sebagai radius A, or if we change the object here, so kita namakan jarak yang kedua ni sebagai radius B. So based on moment of inertia, the concept of moment of inertia, the concept of mass, okay, kita sebenarnya moment of inertia tu mass. Mass of what? Mass of this. Mass of the system. So if we name this one as mass 1, this one as mass 2, okay, so mass 1 is actually equal in term of magnitude with mass 2. However, since radius 1 or radius A is longer than radius B, you are going to feel that mass 1 is heavier than mass 2. Although benda ni sama dan berat dia sama. Ini bila pergerakan dekat dalam, sekejap Okay. Alright. This prove that this mass, object 1 dengan object 2 ni dua benda ni, this is actually the same object. So kalau kata mass dia 10 kg, okay, object 1 is 10 kg, object 2 pun 10 kg, this one. However, in rotational movement, if the radius is longer, this 10 kg is going to feel a lot heavier when the radius is more. Itu ialah moment of inertia. Moment of inertia. Okay, which we can write as I equals to mk square. Okay, kadang-kadang kamu jumpa I equals to mr square. Okay, so what is the difference between K and R? R is known as radius of rotation. In other words, when we talk rotation, when we talk about radius of rotation, it does not change. It does not change. For example, kita ada kayu golf. Length ni takkan pernah berubah. R. But human movement, we always use K, which representing radius of gyration. Okay, dia menunjukkan radius of gyration. So what is radius of gyration? Radius of gyration is still the same. It is actually radius. Okay, it is actually radius. However, those body part can change in term of placement. Macam ni. Okay, kita ada dua ni. Kaki ni. It's still, let's say lah, kita assume kaki ni seberat 10 kilo. Okay, one leg is 10 kg. But 10 kg in posisi A, this is posisi A lah kita namakan, and 10 kg in position B is going to be different when you start swing the leg. Okay, when you start swinging the leg, it's going to feel different. If the radius of gyration is smaller, it will be what we call it less weight compared to if the radius is longer. Kaki still lagi 10 kg. Okay, now let's prove that. Kita ambil dua kondisi ni, okay? So the first condition is your leg like this. The second condition is your leg like that. And the axis of rotation will be the head of the femur. Okay. So radius of gyration, we are going to take from the axis of rotation to the middle of the part, to the middle of that particular peripheral. Untuk kaki ni, we can divide this into three, which is the thigh, the lower leg, and the feet. Sama lah dekat sini. The thigh, the lower leg, and the feet. So for radius of gyration, in order for us to determine the whole mass of this leg during rotation. Okay, during rotation. Kalau without rotation, we just measuring dia punya mass. Okay, let's say mass untuk kaki ni 10 kg. However, during rotation, it's going to be different. Okay, so how we want to determine that? First, we are going to take the midpoint of those peripheral part. Okay, contoh kita ambil 1, 2, 3. Okay, and then we are going to connect the midline to the axis. This one is known as K1. Okay, for the lower leg from the midline to the axis, this is K2. And the third one from the feet to the axis, this is K3. Same goes here. So we have K1, we have K2, and we have K3. Okay, now let's imagine K1 roughly around, let's say, 15 cm. K2 around 35 cm. Wah, pendek boleh lah. K3 is around 45 cm. Okay, untuk yang ini pula, K1 it will be similar, but K2 is not. Okay, K2 now maybe we put it as 60 cm. And K3, 90 cm. Okay. So, to determine the weight of the system during movement, during rotational movement, dia hayun kaki dia kan, kita nak tahu mana lagi berat. Okay. To know that, we are going to use I equals to mk square. Okay. And since we have 3, dia ialah I equal to summation of all mk square. Sama dengan mk1 square plus mk2 square plus mk3 square. Same goes here. I equals to summation of mk square. Okay. Jadi mari kita cuba buat where the k, all of this need to be changed into meter first lah. It will become 0.15, 0.3, 0.45. This one will become 0.15, 0.6, 0.9. Okay, cuba kita selesaikan. Alright, now we have M will be 10, okay, and then K will be 0.15 square. That is the first part, the thigh, and then for the lower leg is 10, 0.3 square plus the feet, it will be 10, 0.45 square. Okay, here we have 10, 0.15 square plus 10, 0.6 square plus 10, 0.9 square. Okay, cuba selesaikan. Berapa kita dapat? How much I moment of inertia we have here, how much moment of inertia we have here. Kita namakan I1 and I2. Cuba. Okay, how much you have it? .15 square times 10, it will be 0.225, 0.23 plus 0.3 square times 10.9 plus 0.45 square, 2.03. Okay, 2.03 plus 0.9 plus 0.23, we have 3.16 kg. Okay, apa lagi kita ada kat sini? It will be kg, this will be m, kgm square. Okay, and as for this one, we have 0.23 plus 0.6 square, it will be 3.6 plus 0.9 square, it will be 8.1. So plus 3.6 plus 0.23, 11.93 kgm square. Now, berat kaki linearly is 10 kg. However, when you start swinging with a longer range or radius, it will end up 11.93 kgm square, meaning that the moment of inertia or the mass of this leg during swinging is actually more than the mass of the leg linearly. Same goes when we bend the leg. Since the leg is the radius is shorter, instead of getting 10 kg during the swing, it become only 3 kg, meaning that you can have much faster movement of the leg during during bending of the leg. Ni moment of inertia. So here we prove that in rotational movement, radius play a major role, where if the radius of rotation is longer, you are going to use much more energy in order to in order to do the same action compared when the radius is shorter. So when we try to do a fast action, especially in rotational movement, we need to ensure that the radius is actually shorter, and then you are going to use less energy. Or in other words, if you invest the same amount of energy, you can have much faster action with shorter range of motion. Shorter range of motion with shorter radius of the motion itself. Ini adalah konsep moment of inertia. Okay, moment of inertia ataupun berat sesuatu objek during rotational or during angular motion. That is the first one. Okay, so from that we go to angular momentum, and angular momentum is quite similar as the linear momentum, where momentum represent the amount of movement you have in the system. Bola yang kena sepak ada momentum. Why dia bergerak? So anything that move has momentum. Okay, except in linear, this is what we call momentum. We imply impulse. Okay, we deliver force. We have collision between our leg and the ball, which means that we imply an amount of impulse to the ball, causing the ball to have velocity. And when a ball have a velocity, it will move. Okay, it will move. And this move is caused by momentum. Move forward. However, for an object, okay, where you have an axis of rotation, and you apply an amount of force, it will cause movement. But this movement is rotational. Ini angular momentum. How much movement have by a system rotationally? Okay. So in linear, it caused by force. In angular, it also caused by force. But this force is known as torque. Okay, it is known as torque. Alright. So why it is torque? Because a force that causes rotational movement is known as torque. Okay, it can be T equals to F D. Dia ada D ni. This D is actually the distance between force and axis. Okay, tu kena faham tu dulu. Okay, torque is a force being given to an object where it is not directly to the axis of rotation. If a force being given like this, no rotation going to occur. But when force being given perpendicular to the axis, it will cause rotation. Okay, apa itu distance dia? Alright. So let's say kita ada satu objek macam ni. Okay, the axis of rotation. We give a force. Okay, the distance is this one. When you have line of force, you just elongated the line of force and then draw another line dissecting or this line need to be parallel. Okay, selari dengan line force, but this line need to intersect with the axis of rotation. Ni imaginary line. Okay, and from the axis straight to the force line, you need to have one straight line. This is the perpendicular line. Okay, so this line representing D, the distance between force application to the axis ataupun dia punya radius. Okay, now contoh yang kedua. Let's say instead of giving a straight, we give it diagonally. So dekat mana perpendicular dia? Okay, elongated the line of force and then draw a line parallel, selari, but that line need to intersect with the axis of rotation. And from the axis of rotation, draw a straight line to the force. These are the radius ataupun distance. Tu dia. Okay. Contohlah, katalah distance ni 2 cm. Jadi berapa torque yang kita bagi dekat dalam sistem if the force being given is 40 Newton. So torque equals to Fd. Okay, torque being given equals to Fd. So it will be 40 times 0.02. Okay, 40 kali dengan 0.2. We have 0.8 Newton. Just this much of force subjected to the system. Although the force being given 40 Newton. Okay, ini torque. Okay, this is what we call as torque. Alright. So angular momentum, when we give force to an object, it causes the object to move. When an object moves, dia ada angular momentum. Okay, it will have angular momentum. So in angular momentum, we are going to name it as H. Okay, equals to I omega. I ni moment of inertia. Omega is velocity of the angular. Jadi benda ni kita boleh pecahkan lagi. It can also become mk square omega because mk square is moment of inertia. This is angular momentum. Okay. Jadi, okay, if a ball rotate on its axis, this rotation have angular momentum. Okay, it has angular momentum. Example, if the ball is 500 gram in terms of mass, okay, and then the radius of gyration, let's say the radius here is 5 cm, 10 cm kecil, no, 10 cm, okay, R equals to 10 cm, and the rotational of the object, okay, the omega is 2 radian per second. So how much angular momentum this particular system have? Kamu bolehlah cari. H equals to mq square omega, where m mass 0.5, k 10 cm is 0.1 square, and omega is 2. Okay, 0.1 square times 0.5 times 2. Tu dia 0.01 apa dia? kg. Okay, and then we have meter square. Tu dia. That is the angular momentum. Means that this particular object has a certain amount of movement. Okay. So in sports, why angular momentum is important is because of this principle. Principle of angular momentum conservation. Okay, kita tengok gambar dia dulu. Okay, gambar ni. So in any rotational movement, angular momentum is going to be conserved for every single phases. Dia takkan ada angular momentum yang cepat, dia takkan ada angular momentum yang lambat. So if we name this process phase 1, phase 2, phase 3, phase 4, phase 5. Okay, kita ambil 5 phase. Alright, I'm going to show you one first. This is what we call a full layout. Ataupun kita ambil ready position. This one full layout. This one is tucking. Okay, kita ambil phase 1. Alright, in phase 1, the diver is tend to jump. Okay, jadi kita akan ambil satu point. Let's say we take the mass, we try to determine the mass of the hip region reference to the COG. Okay, ataupun kita ambil, ni nampak terlalu dekat. Kita ambil mass of the leg in reference to COG. Okay, the human mass, okay, katalah jarak ni, okay, this jarak is roughly around, okay, the radius of gyration here is 45 cm. Macam pendek jap boleh lah. Okay, the radius of gyration is 45 cm. Okay, and then the mass of this system, let's say kita ambil mass dia dekat sini, 40 kg. Okay, alright, and then what else do we need here? Angular momentum equals to mk square omega. Alright, and then at an instant of jumping, dalam proses dia nak jumping, the rotational velocity happen to be, kita ambil paling sikit je, okay, 1 radian per second. Okay, so now please let's calculate what do we have in terms of angular momentum here, phase 1. Okay, H1 equals to mk square omega. Omega ni. Angular momentum. Okay, so now let's include all other information where we have 40 kg K square is 0.45 square and omega is 1. 0.45 square times 40 times 1. Okay, kita ada 8.1 kgm square S. Ini momentum dia semasa dia nak lompat. Okay, when we talk about principle of angular momentum, since we have the first angular momentum 8.1, it means that every single action here, the angular momentum is equal, or else kamu akan dapat video yang macam orang tu jatuh tak masuk bentuk yang sepatutnya dia dapat, because maybe at certain point they need to roll, they don't roll. At other point they need to have a full layout, they don't have a full layout, simply because the action is not fluent. Why? Because the angular momentum keep on changing across the phases. Okay, now let's take a look at the second phase. Kita ambil contoh fasa kedua dulu, where we have something like this. Okay, still lagi point yang sama, but now dia punya K dah berbeza. K nombor 2, ni K nombor 1. Let's say K nombor 2 ialah 30 cm. Okay, K2 equals to 30 cm. Now let's calculate omega dia, since angular momentum dia tak berubah. So we have H2 equals to mk square omega. Now the change only going to happen at the omega. Okay, where we have 8.1, 40, 0.3 square omega. So 0.3 square times with 40, we have 3.6. So 8.1 equals to 3.6 omega, where the omega is going to be 8.1 divided with 3.6. We have 2.25 radian per second. This is omega 2. This is omega 1. That is the change that going to happen throughout angular momentum cases. Okay, if the K is larger, the omega is going to be fewer. If the omega is larger, the radius of gyration is going to be smaller. These are angular momentum conservation. So for every single action here, the angular momentum is 8.1, 8.1, 8.1, 8.1, 8.1. But what is changed? Here we have K besar. Due to that, omega kurang. So we can see at this phase, the person is not rotating too much. But throughout tucking phases, we can see that he are going to tuck or she are going to tuck, and the rotation is going to increase in order to counter the radius of rotation. So now let's take another one. Kita ambil tucking yang paling besar. Okay, so tucking yang menyebabkan dia jadi paling kecil. The same point. Now let's imagine K here is 15 cm. Okay, dia tuck rapat. So let's take a look at I3 equals to mk square omega, where I3 is 8.1, M is 40, K is 0.15 square omega. So 0.15 square times 40, we have 0.9. 8.1 equals to 0.9 omega, and omega equals to 8.1 over 0.9. We have 9 radian per second. So it proves that throughout this process, here you have a slowest angular rotation. Here you have slightly higher angular rotation. At the point or at the apex, you're going to get the most angular rotation. But the radius is going to be the shortest. So if we go through forward, we can have a longer radius of rotation compared to here, and the omega is going to be slower, less than 9. Yang ini, dia akan kembali lebih kurang seperti asal. So, if here at the full layout position, you still have a lot of angular rotation, itu yang kamu tak masuk tegak. Instead of that, kamu jatuh terlebih. Mungkin jatuh dekat belakang atau jatuh dekat depan. Because angular motion, rotation, the angular velocity is still there. Okay? Although you actually need to have less and less angular velocity. Itu konsep angular momentum conservation. Okay, where every single phase, the angular momentum value is actually going to be quite similar. And this angular momentum is caused by kawan dia lagi satu, angular impulse. Same as what we have learned before. Okay, bola bowling. Kita baling tangan. Okay, this is tangan. So, kita hayun bola bowling and we release where we inflict impulse. We inflict impulse to the bowling ball, cause the bowling ball to travel. Means it cause the bowling ball to have momentum. Jadi dalam case linear, we have impulse momentum theorem which said that I equals to M. Okay, Ft equals to mv. So same as angular cases. Cuma dalam angular case ni kita boleh tengok lagi banyak benda lah. First, I equals to m. In angular, impulse is written as this one. Okay, and momentum is this one. So impulse in linear is ft, and we know that f in angular is torque, Fd. Jadi angular impulse is F dt equals to angular momentum which is I omega ataupun mk square omega. Ini angular impulse. And angular impulse can also be determined by the change of angular momentum. Sama lah dengan ini. Change of linear momentum. Okay. Change of linear momentum. Sama macam ni. Jadi, angular impulse can also be written as mk square omega final minus mk square omega initial. And it can also be written as mk square alpha. Ni nampak saya dah tertunjuk dulu dah. Because when we talk about change of momentum, it is actually the change of acceleration. So ini adalah perumpamaan untuk angular impulse. So what is angular impulse? Angular impulse is force. Okay. Force being given. Okay. These are torque. So what is impulse? When you give torque in a certain period of time, this is known as angular impulse. Sama lah macam bola tadi, kita apply force. Okay, how long you apply the force, that is impulse, Ft. Jadi, angular impulse is how much force being given in a period of time, which will cause the object to rotate. And this rotation containing angular momentum. Sama je linear dengan angular ni sama. So means when we apply angular impulse to an object, it will cause the object to move angularly. When we apply linear impulse to an object, it will cause the object to move forward. Okay, sampai sini boleh dapat tangkap? Can you understand this one? You okay?
Okay, sir.
Okay. Ni angular impulse. Okay, jadi angular momentum kita sepak bola dia bergerak. Angular impulse kita sepak dia rotate. Because angular movement is just rotation at an axis. Dia tak pergi tempat lain. So lagi banyak angular impulse kita bagi, lagi banyaklah pergerakan ataupun lagi lajulah rotation tadi. For example, we give some force to the clock hand. It cause the clock hand to move. We jentik the clock hand, it cause the clock hand to move faster. So that jentik and that contact cause impulse to the clock hand, and how fast it move, that is angular momentum, H. Okay. Okay, saya bagi contoh. Sekejap ada apa lagi dekat angular momentum. This is an example. Okay, this is one of the example. A force that being given to a body cause the body to do a backward somersault. So kita ada satu center of gravity, that is the axis of rotation, and the force being given is a torque. Okay, kenapa torque? One, force being given upward. Second, weight pull the body downward. Combining these two, torque. You're going to get rotation, a backward somersault rotation. Kalau dia nak ke depan macam mana? Macam mana kita nak jadikan dia ke hadapan? So we change the arrow. Instead of pulling the weight backwards, now we pulling the weight face front. Ke bawah juga. Okay, it's still ke bawah. And you still inflicting force ke atas. So satu force ke atas, satu force ke bawah, forward somersault. Okay, forward somersault. Jadi kenapa kadang-kadang tak jadi somersault? Because the amount of forward force is lesser compared to the amount of upward force. Jadi dia lebih bergerak ke atas dan tidak rotate ke hadapan. Okay. Alright, I'm going to give you an example of impulse. Ini perumpamaan ya. So we have mass, we have movement of inertia, we have force, we have torque, we have momentum, we have angular momentum, and finally we have impulse, we have angular impulse. Ini adalah perumpamaan dia dalam bentuk linear, dalam bentuk angular. Okay, now let's take one. Alright, I think some of these question we have already discussed, but it's okay. Let's discuss it a bit again. Right, let's say we have a racket. Okay, kita ada satu racket, yang mana racket ni, the mass of this racket is 1.1 kg. Linearly timbang 1.1 kg. Okay, and this is the point of grip where we are going to determine this as the axis of rotation. Okay, tempat kita buat flick. Okay, and then during an action, the moment of inertia for this racket noted to be 0.4 kgm squared. Maksudnya masa pergerakan, when you do flicking, the weight of this object is noted to be 0.4 kg. Lagi ringan daripada raket itu. So now the question is, what is its radius of gyration? Dia nak tahu dekat mana dia axis ni. How far is the axis located in reference of the racket cloud, racket face. Berapa jauh? Axis dekat sini ke? Axis dia dekat sini ke? Axis dia dekat sini ke? They want to know how far is the radius of rotation. So from here, you are going to consult the equation of I equals to mk squared, where I is 0.4, m is 1.1, and k kita tak tahu. Dia nak R kan? Okay lah, kita tukar jadi R. Pasal ni kan raket kan tak pernah berubah rupa dia, R square. So we don't know the R square. Jadi cuba selesaikan yang ini dulu. We have R square equals to 0.4 over 1.1, where R equals to 0.4 over 1.1, the square root of that Berapa kita dapat ni? 0.4 divide with 1.1 and the answer we go with the square root 0.6 meter or 60 centimeter. Ni contoh, okay, contoh penggunaan. So they try to determine the point of the radius of gyration. Okay, now let's go to the second one. Alright, and now we talk about angular impulse. Okay, kita ada kaki, we have a swinging leg. Okay, now imagine this leg is swing forward and backward. Okay, how can our leg swing? Muscle mana kita nak activatekan dia untuk swing forward? Which muscles? The upper muscles or the lower muscles? Upper.
Lower.
Lower. Kita nak swing forward. Kita nak swing dia ke atas. Kita activate yang mana? Lower ke?
Dua-dua, sir.
Dua-dua. Depends kan. Sekejap atas, sekejap bawah. Okay, kita ambil satu je lah. Kita ambil satu dulu. Kita ambil satu dulu. Let's say, in order to swing it forward, you are going to activate dia ni. Naik atas je. Belum ke bawah kalau kita freely swing, mungkin sekejap kita activate, sekejap kita loose out. Okay, now we are going to talk about this one first. Okay, let's see this leg swing front and back at a speed of 8 radian per second. Okay, and then the moment of inertia for this complex, maksudnya dia dah tambah semua ni lah. Okay, the moment of inertia of that leg noted to be 0.7 kgm square. Okay, now the question is how much force, okay, how much angular impulse, how much angular impulse needed in order to stop the leg. Okay, maksudnya sekarang kalau kaki ni bergerak, ini adalah kelajuan dia sekarang lah. We name it as omega 1. Dia nak how much impulse, dengan kata lain, how much force we need to put at the leg in order to make the new omega of the leg to be 0. Stop. Okay. Jadi kita nak bergerak, kita gunakan tenaga. We want to stop a thing, we need to apply an energy to, an amount of force. Because if we have something like this, moving forward, kita ada force equals to 10. Kita nak stopkan dia, means kita kena bagi satu lagi force equally, but from different direction. This is impulse in the system. This is impulse given. So, if 10, we add on dengan 10, we end up dengan kosong. No movement. Ini konsep impulse. Okay, this is the concept of impulse. Alright, so from here, how much impulse needed in order to make that 8 radian per second leg stop? Jadi kalau kamu buka balik equation berkenaan dengan angular impulse that I have been given to you, okay, kita ada impulse is change of momentum. Impulse is change of momentum. Okay, kenapa kita nak kena pakai change of momentum? Okay, alright. Because change of momentum is I omega 2 minus I omega 1. We have I. We have omega. That is the reason why. Okay, that is the reason why. Kenapa kita tak pakai impulse equals to F dt? Do we have F? No. Do we have T? No. And that is how you choose which equation want to be used. Okay, so now we have angular impulse equals to I omega 2 minus I omega 1, where I is 0.7, omega 2 dia kosong. Okay, minus I 0.7, omega 1 dia 8. 0.7 kali 0 habis. 0.7 kali 8 5.6 negative. That is the amount of impulse needed in order to stop the leak. Okay. Inilah amount of impulse yang kita perlukan untuk berhentikan kaki itu. Okay, soalan saya yang kedua. How much angular momentum does this leg have during ini? During masa dia berayun tu, berapa banyak angular momentum dia ada? This is tricky question. You don't need to calculate anything here. How much angular momentum the system have during movement? Where you know in order to stop that, we need negative 5.6 kgms squared.
5.6 juga, sir.
Ya, 5.6 juga. Tapi apa yang beza?
Dia positif lah sebab dia bentangan arah.
Betul. Dia positif sebab dia bertentangan arah. And that is the reason why we give negative 5.6 in order to stop. That is correct. Okay. Itulah konsep impulse. Okay. So impulse cause movement. Okay. Linear impulse cause linear momentum. Angular impulse cause angular momentum. Okay. Now let's move on to another example. Banyak pula pagi-pagi buta begini. Alright. This one is about, okay. Alright, yang ni tak susah sangat. Okay, let's say we have a volleyball player hand. Okay, tangan volleyball player. Okay, katalah ni bola dia. Okay, this hand is moving in rotation. Okay, move at the shoulder point. Alright. This hand, the mass of this hand is 3.7 kg. Okay, this is mass linearly. And this hand move at an angular velocity of 15 radian per second in order to execute a spike. Jadi kalau kata executing spike, pergerakan tangan dia macam ni lah. Okay, they try to do a spike. So the hand rotate like that. Okay, if the average moment of inertia during this rotational action, the moment of inertia of the hand noted to be 0.45 kgm squared. Okay, so the question is, what is the radius of gyration? What is this? Tangan dia tegak ke? Tangan dia bengkok. What is the radius of gyration? Okay, so you have I. We try to find out K. Jadi equation yang paling sesuai is MK square. MK square. I equals to MK square. Kita nak tahu K je. Jadi kenapa dia bagi kita radius tadi? Kenapa dia bagi kita omega? Itu untuk mengaburi mata pihak lawan. Okay. We don't need to use that omega pun sebenarnya. We just need to find out K. So I equals to 0.45, M equals to 3.7, and K we try to find out. Jadi K ialah 0.45 over 3.7 and the square root of it. Itulah jawapan untuk K. Berapa kita dapat? Square root 0.35 meter ataupun 35 cm, meaning that the hand is quite flat in position rather than tegak. Okay, itu maksud dia. Okay, sampai sini okay?
Okay, sir.
Okay, now let's move on to this one is regarding principle of angular momentum conservation. Okay, we have a diver. Ni case diver macam tadi Diver tu dah ready nak lompat. This diver, the mass of this diver is 50 kg. Okay, full layout. And when we take the radius of gyration, let's take a radius of gyration with respect to her transverse principle. Okay, maksudnya dia ambil something like this. Dia ambil titik tengah. Okay, and then dia ambil tengah-tengah berat dia. Okay, so this transverse plane K equals to 0.45 meter. Okay, and this person jump with a radius, with a velocity of 6 radius per second. Ni phase 1. Soalan dia, masa dia dekat dalam takik, okay, phase 2, where the radius being changed from 0.45 to 0.25. Okay, daripada 0.45 jadi 0.25. Soalan dia, at this phase, how fast does this diver go? Sini 6 radian, maksudnya tak adalah laju sangat dia punya rotate. But we know that at this position, the rotation is going to be intense. So the question is, how much? So to solve this one, first, we need to find out H1 and use H1 in H2. H ni apa? Angular momentum. mk square omega, where k here is k1. Ni k2. Okay, and here kita akan pakai mk square omega is k2. Okay, so H1 berapa? 50, 0.45 square, 6. 0.45 square times 50 times 6. The momentum here is 60.75 kgm square s. Jadi, since principle of momentum conservation, H1 is always equal with H2. So we have 60.75 here. The m does not change, but the k do change. Omega. We try to find out the omega. Jadi omega dia ialah 60 bahagi 50 0.25 kuasa 2. .125 bagi 3.125. We have 19.2 radian per second. Maksudnya dekat sini tadi kalau dia berpusing lah, kalau kita assume kan dia punya pusingan macam ni je lajunya. But here macam dah laju lah pusingan dia. That is principle of angular momentum conservation. When we have less omega, longer radius. When we reduce the radius of rotation, omega automatically will increase. Okay, itu adalah benda yang sama seperti apa yang kita pernah tengok sebelum ini di sini. Okay. Control click. Ni benda yang sama. Inilah principle of angular momentum conservation with the aid of moment of inertia. Kalau kamu lupa. Okay.
What I'm going to do is I'm going to stand on that. Weights out. When I hold these weights out like this.
Rotation is angular momentum. Okay. Rotation is angular momentum. So now, the movement is angular momentum. Okay. Rotation tu kita boleh ceritakan dalam bentuk angular velocity, and how the weight being distributed is actually dia punya placement of weight, radius of rotation. If radius of rotation big, Okay, longer radius of rotation, lesser angular velocity. And if we reduce the radius of rotation, less k, we are going to increase omega. Along the way, those two conditions have the same amount of angular momentum.
This, I'm going to spin like this. When I hold them out far, do I have a lot of rotational inertia or a little? How about when I pull them in? A little? So if I get here rotating like this, and I hold them out, what happens when I pull them in? Ooh. Easier to rotate, gang. Harder to rotate. Easier to rotate. Harder.
Okay, itu konsep dia. Okay, this is the concept that being visualized based on the principle of angular momentum, moment of inertia, and also angular impulse. Ni konsep dia lah. Kita tunjuk secara terang. Okay, ada soalan? Do you have any question? Ada beberapa contoh lagi ni kat sini. Any question, guys?
No, sir.
Sekejap Okay. Kita tengok lagi dua, tiga contoh. Lepas tu, we end the class. Alright. Now is an example in the sport of tennis. Oh, ada satu subtopik lagi lepas ni. Sekejap We have, let's say we have a tennis ball. Alah, ini susah sangat nombor dia halus. Okay. The forearm flexor. Okay. So let's say this is an example of your hand holding an object. Okay, so the question is, what is the resulting angular acceleration of a 1.7 kg forearm and hand? Okay, kita ambil ni je. Forearm and hand. The mass of this system is 1.7 kg. Okay. Question dia nak kita cari angular acceleration. When the forearm flexor attaching 3 cm from the center of rotation at the elbow. So this will be the axis of rotation. And then we have the forearm flexor, so the upper muscles. Okay, flexor. Attach here. Okay, and the distance between the axis and the attachment is 0.03 meter or 3 cm. Produce, okay, and this flexion produce a force of 10 Newton. And the angle is 90 degree. Yalah, angle ni angle tegak lah maksud dia. Okay, kalau angle tegak ni kita tak payah buat apa-apa sangat. And the elbow and forearm, hand, okay. And finally, the midpoint, okay, ataupun radius of gyration for this is 20 cm. So the question is, how fast? Bila dia flex, zas, dia naik atas. Berapa laju pecutan tangan itu? Okay. So to do this, we are going to consult with an equation of torque equals to I. Tadi kita ada I omega kan? Okay, so now we have torque equals to I alpha. Kalau kita mudahkan lagi, kita akan ada FD equals to MK square alpha. Okay, ni sama. Equation ni adalah equation yang sama dengan MK square omega. It is also torque. Alright. Now, let's take a look what information we have. We have F produced by the flexor, which is 10. And D is the distance between force and axis. So since this is a 90 degree parallel force, so we just take the distance as a whole. Kerana force ini dibagi tegak. Maksudnya macam ni. Okay. Ni radius. So the force and radius is straight. Dua-dua sama arah. So this is not the case of projectile, not the case of angle. This is a straight. Jadi kita ambil terus 0.03. Okay, and then mass of the object 1.7. K, the radius of gyration for this particular system 0.2 square and alpha. Dah boleh selesaikan. So we have alpha equals to 10 times 0.03 divide with 1.7 times 0.02 square. Berapa kita dapat ni? 0.3 bahagi 0.2 square kali 1.7. 0.028. 0.3 bahagi 0.028. Kita dapat kat mana saya salah ni? Sekejap, saya ada kesilapan teknikal. 0.02 square, okay, times with 1.7. 0.068, bukan 28, bagi. Jadi 0.3 bahagi dengan 0.068, we have 4.4 radian per second square. Meaning that by giving 10 Newton at the flexor, the hand is going to accelerate. Okay, the rotation is going to accelerate at a pace of 4.4 radian per second square. Okay, contoh nombor 2 dia ada tricky sikit. Okay, ingat yang ni. If the case is 90 degree and then distance dia we take as a whole. Okay, the second case is we have a leg. Okay, and then we have our patella tendon. Okay, we have a tendon attached to the tibia, patella tendon, and it attached at an angle of 20 degree, 3 cm from the axis. Okay, maksudnya ni axis. Okay, the distance is 3 cm. And attachment dia ni, attachment dia macam ni. Dia attach macam ni. Means that there are theta, and the theta is 20 degree. Case yang tadi, attach dia dekat sini. So it is parallel with the axis. But now, axis here and the attachment is angular. Now we have angle. Okay, ingat yang tu dulu. Okay, so the patella tendon attached to the tibia at 20 degree, 3 cm from the axis of rotation. Let's say, if this tendon giving out a force of 400 Newton, okay, force being delivered 400 Newton, and the lower leg, okay, this system, the mass is 4.2 kg. Okay, the mass of the system is 4.2 kg, and radius of gyration, so the midpoint of the system is 25 cm. So the question is, how fast? Okay, the question is, what is the resulting acceleration? Means when 400 Newton being given, how fast the leg is going to rotate. Case yang sama macam tadi, where we have torque, okay, ni rotational ni torque equals to I alpha. So torque is Fd equals to mk square alpha. Now the tricky part is actually here. F tak susah, 400. Okay, sorry, 400 pula. Salah tempat, boh. F F ni yang kita kena tengok. Okay. So since F macam ni kan, bila kita tengok gambar ni, F being given like this. It being given in angle. It has an angle of attack. Sini F being given at 90 degrees. So no angle of attack. It is straight to the point. Here, no, it being given in an angle of attack. So F here, kalau kita keluarkan gambar rajah ni macam ni kan, mungkin gambar rajah menyongsang tu susah nak faham. We change the landscape of the pictures. Macam ni. So this is F. Projectile. Ada angle. Means that this hypotenuse, okay, this hypotenuse is actually the derivation of both opposite and adjacent. Jadi kita nak bahagian ini, so we need to include bahagian O sekali. So if you face any problem like this, always remember F here is F sin theta and then D. Yang lain semua sama because it include an angle, means the force is not straight, the force is angular. So kamu akan ada 400 sin 20 and the D is equal sama yang ada 0.03, M is 4.2, K is 0.25 square and finally alpha. Selesaikanlah satu-satu. We have 20 sin kali dengan 400 kali dengan 0.03, 4.10. And then 0.25 square times 4.2. We have 0.0125 alpha. Automatically, alpha equals to 410 divide 0.0125. Sekejap macam terlebih perahu ni. Sin 20 K kali dengan force 400 K kali dengan D 3 cm 0.03 K 4.10. Alright, and then we have 4.2 and 0.25 K 0.25 square times 4.2. Betul. 0.263. Sorry. 263. Okay. So 4.10 divide with 0.263. 15.59 sama dengan 15.59 radian per second square. So by having 400 Newton pulling the leg, it will cause a torque to occurs and this leg is going to accelerate angularly at 15.59 radian per second square. Jadi dua case ni berbeza dekat angle of attack je. If the angle of attack is parallel, is straight, you don't need to include sin because the force being delivered straight. But if the force being delivered at an angle, the amount of force is not going to be equal as the amount of force being generated. Generated 400 Newton, but within an angle, dia akan turun. Dia takkan dapat 400 lagi. Dia akan dapat 100 lebih je tadi kan, sin 20 kali dengan 400. Okay, this is a case of angular momentum and also angular impulse. Okay, so let's go to the last topic. Ada soalan?
Sir?
Yes.
Meaning yang F sin theta tu,
Okay.
dia digunakan ketika bukan 90 darjah ke macam mana? Bukan 90 darjah lah kiranya.
Bukan 90 darjah. When you see bukan 90 darjah, bila dia kata okay, Katalah kamu dapat contoh macam ni kan, dia bagi soalan force apply 30 degree. Maksudnya sekarang force tu dia apply macam ni. Force 30 degree. So bila kita nampak case macam ni, katalah force ni 10 Newton, when you see 10 Newton here, meaning that this is actually a derivation of dua arah hypotenuse ni. It include vertical. Tapi 10 Newton tadi, 10 Newton linear. Kita tak include lagi vertical. So to include vertically, kita kena pakai seat. Jadi kebanyakan case human movement where the force where the muscles architecture is pennant. Ingat lagi tak tu? Muscle architecture. You still remember this one? Kita ada parallel muscle, kita ada penetration muscle. Ingat ke tak ingat?
Ingat saya.
Bila case penetration muscle, dia memang force being applied at an angle. So always use this. Jadi F dia bukan F semata. F dia ialah F sin theta. Tu dia.
Oh, okay.
Kalau dia kata force applied 90 degree, tak payahlah. Because force tu memang tegak. Tapi kalau kata force deviate 20 degree from the midline, maksudnya dia deviate. So force tadi sepatutnya 20. Tapi kita kena cari resultant. Ni bila ada cerita degree je, this force, we need to find out dia punya resultant. And in order to find resultant, ada dua je cara. One is by using F sin theta. Another one is by using F cos theta. Ada dua je cara. Okay. Most of the time, if the problem involve force generation, ini dia. Yang ini kan, F cos theta ni is involving force being applied macam ni. Force being applied in a projectile, but we try to find out dia punya how far. Horizontal cases, cos theta. Vertical cases, sin theta. So muscle architecture, most of it is vertical cases. Most of it is penetration. Most of it is force being applied at an angle. Jadi dia akan pakai force sin theta. Jarang-jarang lah. Yang ini selalu dia akan sebut lah find the range. Find how far. Dia force being applied to a certain degree and try to find how far it goes cos theta. Tapi kalau dia kata, dia bagi tahu, okay, force being applied here, how much force, how much to, how much this, not range, sin theta. Okay?
Okay, sir. Thank you, sir.
Alright. Okay, the last part is regarding impact. Impact ni benda ni. Jangan sakit kepala, impact ni benda ni. Kan tadi kita ada bola, we have a ball, we kick the ball, we apply external force and we kick the ball. We imply impulse. So, when the leg hit the ball, this is known as collision. So, in collision, there are only two categories. One known as plastic, one known as elastic collision. Okay, pelanggaran. What is plastic collision? You have something, you drop on the floor, and when it hit the floor, collision occurs, the thing change in shape. It does not bounce back. It does not have any more kinetic energy, and the amount of force inside the system dissipate. Dia berubah. But if you have an object, you release it, it goes with the collision and it bounce back and retain the same object. But ada return means that ada kinetic energy. The shape remain, meaning that amount of force being restored. These two, if this is the case, this is known as elastic collision. If this is the case, it is known as plastic collision. Contoh, kamu sepak bola, bola retain, that is elastic. Kamu sepak tembikai, tembikai berubah bentuk, that is plastic. Tu beza dia. Kamu sepak muka orang, depends. Kadang-kadang muka dia pecah, kadang-kadang tak pecah. Muka pecah, plastik. Muka tak pecah, some sort of elastic. Okay. The fact is that, in order to determine plastic and elastic impact, collision, we are going to use coefficient. E nama dia. Okay, this coefficient is named as coefficient of restitution. Coefficient of restitution. Okay, where in this coefficient of restitution, it is actually a calculation that will give you a numbers. The numbers is 1 and 0. So you can fall in between this saja. If the numbers is lesser than or nearing 0, we are going to call that collision as plastic or near to plastic. Tapi kalau dia dapat betul-betul kosong, that is perfect plastic. And vice versa, if the collision coefficient yield a numbers nearing to 1, it is known as elastic. Ataupun kalau dia dapat 1 terus, perfect elastic. Okay, so in order to find out coefficient of restitution, there are two ways. The first one, we use this equation equals to V1 minus V2 U1 minus U2, where 1 and 2 is actually the object. Okay, 1 tu bola, 2 tu bola baling. Betul lah. V is the final value and U is the initial value. Velocity. Okay, maksudnya 2 bola ni kan. Macam tu. So this is object 1, this is object 2. Okay, ni dia datang. So this is U1, this is U2. And then when collision occurs, it goes different. So this is V1, this is V2. Ni cara pertama. Atau cara kedua, okay, we are going to have something like this. Height drop divide height bounce square root. Okay. Ini ada contoh ni. Jap. Jadi depends lah kalau kata equation tu pakai height laju, use the first one. But if the equation use height, use the second one. Dua-dua tu sama bagi benda yang sama. Sekejap distance. One is force. Collision. Okay. Sorry, terbalik. Height bounce, height drop. Where H equals to height, B bounce, D drop. Okay, contoh. Kita ada bola tadi. We drop the ball, let's say 2 meter. And then the ball bounce back at 0.98 meter. Now try to determine the category of collision. So E equals to height bounce over height drop. Square root equals to height bounce is 0.98, height drop is 2 meter, square root of it, 0.98 divided by 2, we have 0.49 square root, 0.7. Jadi kita tahu it is nearing to 1. This is an elastic impact. So how about this? Kita drop 2 and then the ball bounce at 0.3 meter. Okay. E2. Ni E1. 0.3 divided by 2 square root of it. 0.3 divided by 2 square root. 0.38. 0.4. So we know that this one is nearing to plastic. This one nearing to elastic. Contoh mungkin ni bola sepak. Yang ini kita nak bagi apa? Bounce sikit je. Temikai. Okay, mungkin temikai. Okay, mungkin bukan temikai merah, temikai susu lah. Dia bounce lah sikit. Okay, why it does not bounce high? Simply because after collide with the floor, the fruit actually change in shape and we can actually see just a small amount of bounce, not a higher one. The kinetic energy loss the force stored in the system lost, and we got a total change in terms of the shape of the system itself. Itu plastic collision. Kalau elastic, it retain everything after the collision. Alright, so that will be the end of our class for today.